All right, welcome back, everybody. So the last piece that we are going to add to our model for rotational motion is called angular momentum. The way that we are going to get it is actually the same way that we got regular translational momentum back in Physics 211. We are going to look at Newton's second law. In this case, we're going to look at Newton's second law for rotation, which says that the net torque on a system is equal to the moment of inertia times alpha, which is the angular acceleration. And what we're going to do is we're going to leverage the fact that we remember that alpha is the derivative of omega with respect to time, like so. And for most reasonable objects, the moment of inertia is not going to change, right? If I have this tennis ball, pretty much no matter what I do with it, its moment of inertia is not going to change. Under that condition, I can pop this moment of inertia inside of the derivative, and I have d by dt of I times omega, and we are going to define that quantity as the angular momentum, which we will use capital L to represent, of the object or system. So if you know the moment of inertia of something, you know its angular velocity, then you also know its angular momentum by multiplying them together. And you can see that that kind of parallels the translational momentum, right? P was equal to the mass of something times its velocity. So you can see that we have very much just upgraded the regular momentum to get the angular momentum. And of course, we can then rewrite Newton's second law for rotation as a conservation statement, that the net torque is going to be equal to the change in momentum with respect to time. And then furthermore, if there were no net torque on your system, the change in the angular momentum would be 0, and then you might decide to say that the angular momentum is conserved. But just like for momentum, you can only say that if you have found a system where the net torque is 0. So you have to make sure, if you're using angular momentum, that the net torque is 0 and make a convincing argument. There's one other really interesting way that we can think about angular momentum. Because this is a good way to calculate, say, the angular momentum of this ball as it spins and rotates, right? I can easily look up the moment of inertia, and I can easily calculate what the angular velocity is. But there's other kinds of rotational motion, right? Something that is going around in a circle like this, kind of like the moon going around the Earth, or actually even something that is just moving in a straight line is kind of has a angular sense to it, which might seem a little bit weird the first time that you think about it. A good example here is, like I said, the moon going around the Earth. The moon is moving in a circle, but at any moment in time, it's not moving in a circle, it's moving in a straight line, right? And it's the force between the Earth and the moon that causes it to bend around in that orbit. And so even something that's moving in a straight line has angular momentum. And the way that you can write that angular momentum down is to take the cross product between the radius vector, the distance from your origin of coordinates to your object, and your momentum. So for this example here, I've got the moon going around the Earth, for example, where I'm using my hand to represent the Earth here. At any given point in space, maybe I'll pick this one, I can take the radius vector, which is going to point from my hand, from the Earth to the moon, crossed with the momentum vector, the translational momentum vector, which is going to point that way if the moon's going around like so. I take the cross product between those two things, and that will give me the angular momentum of the moon due to its motion around the Earth. And you can actually have both of these things going on at once, right? The moon actually rotates a little bit on its axis. It also is going around the Earth, so you can have both of those things going on at the same time. We'll do a similar example in class this week.